If there is one constant in technology, it's that we always want things to go a little bit faster. And you would certainly guess from the name Rapid Spanning Tree Protocol that that's what RSTP is all about. STP does a fantastic job for us at blocking switching loops before they happen. But there are times when we'd like it to operate a little bit faster, and that's when RSTP can come into play for you. Now, this particular video, we're going to be going through the theory of RSTP, and the thing is, almost all of the STP concepts carry over. You know, the root bridge election, all that stuff. The port roles can be a little bit different. We're going to see that in a walkthrough and a live lab coming up in another video. And RSTP, whenever you see 802.1W, we're talking about RSTP, and that is considered an extension of 802.1D, which is plain old or good old spanning tree protocol. Now, where the rapid part comes in, you know, that 30-second delay that we have built into STP convergence through the listening and learning states, that's still acceptable to a lot of networks. Plenty of networks will run STP, and I don't want to make it sound like, you know, it's something old and dilapidated and just way too slow. But RSTP does make things a little bit, well, a little bit more rapid, especially at certain points in our network. And you'll see exactly what we're talking about as we go through this theory. Now, again, the overall concept of the root bridge, it's still here in RSTP. You still have elections the same old way, but the port roles are a little bit different. We have some new ones, and we're going to see those where in our next walkthrough, where switch 1 is the root. And note that in this particular network, and you might want to write this one out, it's a little odd, switch 3 is going to have multiple connections to the Ethernet segment. And the root and DPs have already been selected, and yes, there is a hub in here. And those of you who have taken courses from me before, and I thank you for that, you know, I really like working real world scenarios in as often as I possibly can, because I don't want you to just pass the exam. Obviously, that's important, but I like you to see some things in the real world as well that don't always go along with theory. But this is not one of them. This is about as anti-real world as you're going to get. You're going to bump into something like this one day, I guess. But the reason I have it in here is to illustrate one particular kind of port that is unique to RSTP. Now, again, the election is really the same. Switch 1 is the root. We know the root bridge is never going to have root ports, and all of the ports on the root bridge will be in forwarding mode. So both fast Ethernet 2 and 3 on switch 1 are designated ports, and they are forwarding. Switch 2 has chosen its root port, so has switch 3, but we got 3 other ports over here connected to a hub where we need to figure out what the port roles are. Now, we know from previous studies when we had that shared segment between the two non-roots in the STP section, one of those is going to end up being the designated port. And the non-root switches, you know, first they'll select their root port, and which they've already done here, and then the RSTP-enabled root bridges will have designated ports just like STP. And what happens there, you know, the two switches have an election, and in this case, as you'd expect, the designated port will be the port with the lowest root path cost of all the ports on that segment. We're going to assume that to be one of the two ports switch 3 has connected to that segment. So fast Ethernet 4 is now the designated port for the shared segment between switches 2 and 3. So what about these other two ports? You would expect those just to go into blocking mode most likely, and that would be it. And with RSTP, it's going to be a little bit different. What happens with switch 2 is instead of putting the port into blocking mode, the port goes into what we call alternate mode. It becomes an alternate port. And alternate here is referring to the fact that this port has an alternate path to the root switch than the one the actual root port does. So if switch 2's port then becomes the alternate port, what about fast Ethernet 5 down on switch 3? It actually becomes a backup port, which is another port unique to RSTP. And this port, you know, again, the name is the recipe. It's a backup port. This port gives switch 3 a redundant path on that segment without guaranteeing that the root switch will still be accessible. So again, not a real world situation here. It's one I brought to you simply to demonstrate when the alternate and backup port roles would come into play. Now, I want to talk about these states here for a few minutes because obviously that's important stuff. And the STP port states, the first 3, disabled, blocking, and listening, they're actually combined into the RSTP state discarding, which is the official initial RSTP port state, the very first one. Now, an RSTP port will transition from discarding to learning, where the incoming frames are discarded, but the MAC addresses are being learned by the switch. Finally, if all goes well, the RSTP port transitions to the forwarding state, which is the equivalent of STP's forwarding state. So just to put those two side by side, we've got STP, disabled, blocking, listening, learning, forwarding, RSTP, discarding, learning, and forwarding. The slightly frustrating thing about this when you're first learning RSTP is that you'll see in the lab that even when we go on our switches, we enable RSTP, we're not going to see the discarding state. You're still just going to see blocking, learning, and forwarding. So that gets a little frustrating because even when you're running your show spanning commands, which we'll certainly do, even if you're running RSTP, the ports kind of look like you're just running STP. It's the timers that really come into play. Now, we'll see that in action, but first, before we do that, I want to go over these two particular port types, edge ports and point-to-point ports. And with RSTP, a point-to-point port is simply any port running in full duplex mode. That's it. And any port that's running half duplex is considered a shared port and has to run STP instead of RSTP. So the point-to-point ports, not that big a deal, but the edge ports are, and this is where it would come in. Now, if the port on the switch is running RSTP and we make it an edge port plays a huge part in RSTP's determination of when a topology change takes place. Now, RSTP considers a topology change to have occurred when a port moves into forwarding mode, makes perfect sense, unless that port is an edge port. Now, RSTP does not consider that to be a change in the network since only a single host would be connected to an edge port. Now, this is hardly an earth-shattering change to our network. And one of the big changes between STP and RSTP doesn't even bother alerting the rest of the network about it. Why bother? You got an edge port there. Who's the edge port affecting when it goes to forwarding? One host. It's not even affecting another switch. So switch 2 would just say, hey, I'm not sending out any kind of notification at all. And I'm using the word notification there for a reason, because when a non-edge port goes into forwarding mode, that's when RSTP does bother letting the rest of the network know. And this is another BPDU type. It's a topology change notification type, and again, the name is the recipe, usually referred to as just a TCN BPDU. And what RSTP would do in that case is send that BPDU type out all non-edge designated ports. So all of a sudden when a non-edge port goes to forwarding, switch 2 says, hey, I'm going to send out a TCN BPDU and let the downstream switch know about it. Now what happens in that case, of course, is that the downstream switch gets it and says, oh, okay, here's a change in the network. I'll send out this TCN BPDU. And it's a ripple effect, really, like when you throw a rock into water, and it just keeps on rippling out. That's exactly what happens here. The change notification is rippled out, if you will, to the rest of the network. But again, with RSTP, that's only going to happen when a non-edge port goes to forwarding. When an edge port goes to forwarding, RSTP just couldn't care less. It's not going to bother notifying the rest of the network. Whew. I know, that's a lot of theory. We got a little bit more we need to go over next, and then we'll do a bit of a live demo and move on from there.